Yeah, I'm Christopher Elash. I'm a PhD student at the University of Saskatchewan, and so that's in Canada for those of you who don't know. So I'll talk about our rad-tolerant microcontroller that we designed. So a bit of a motivation. So the RISC-V ISA has made some big strides in the past few years for the space industry. So I think this conference is a really good example of that. But in terms of reliability, single event effects is still a huge issue for the community, and it kind of gets worse every single year as we try to shrink down to smaller and smaller technology nodes. So we just need a lot more work to understand how to best harden these devices and how best to evaluate them for usage in space. So I have too many slides. I'm really going to rip through this here, so I apologize if it goes by quick. So a bit of an introduction and background for the radiation effects. So for digital systems, these transient pulses that are developed by these radioactive particles that strike the devices, they can manifest into what we call these bit flips or single event upsets. So in the case of a storage latch, if you get this transient pulse that strikes in the back-to-back loop inverter here, that transient can get it can get latched within the storage cell, and then you get this bit flip. So for complex devices like microcontrollers, processors, this sort of thing, it can just result in just a wide variety of issues that you just don't want happening for your space mission, like just data's corrupted, jumps in the program, like the horrible blue screen of death. These are things we just do not want. And so for radiation environments, like the community, many companies provide these devices that are supposed to mitigate and reduce the likelihood of these errors occurring while in space. So on the market now, I mean, there's a wide number of rad hardened or rad tolerant devices you can pick. I just kind of went ahead and just picked 3 of them that I knew from beforehand. So usually when you look at the data sheet, you get some sort of total dose rating number, you get a single event latch up number, and then the clock speeds are for space that we want them to be faster. We want to go faster, right? So there's some issues with this because that most of the consumer devices are still running ARM. This is a RISC-V conference. You want to use RISC-V. And then the other issue is that in terms of the SEU performance data, it's really limited. It's not provided for the devices. How is it tested? And then also how is the devices hardened? How did they get those numbers? It's almost never given. So we want more information. So going back to our device here. So our device we've entitled Star RISC is the name we've given it. So we've taped this out on 22 nanometer FDSOI, and it relies on the open source Core 5 MCU project from Open Hardware. So it features a small and efficient 32-bit core, and it's open source. You can go to the GitHub, you can go look at it, and it has some configurable options. And so in terms of our device, so it's a full system on a chip. So we have memory on board that's protected with ECC. There's peripheral connections, there's internal SEU counters, timers, a lot of different things that you can play around with the device. So it's pretty fully fledged. And it's supported by a development kit board. So it has access to all the different peripherals, all the different functionality, bells and whistles that you want to play around with. It even has an ESP32 if you want to try and connect it to Amazon Web Services and do some sort of edge computing or something. So there's a lot of things you can do with it. Our device is there in the middle, you can see. And it's also supported with an Eclipse-based SDK, thanks to Open Hardware with GCC support. So it's quite easy to use and work with. So in terms of hardening the device, there's a number of things that we do. I know a lot of the talks have been talking about this TMR approach, redundancy, this sort of thing. We take an entirely different approach. We don't do any of this. So inherently, the device is built on 22 nanometer, and this node is just inherently really good against single event effects because of this small active area in the transistors and this buried oxide layer, which electrically isolates the transistors. It just becomes really good in terms of mitigating single event effects. Of course, talk about there's the ECC memory on the SRAM that's in the device. We have some counters to monitor single and double bit upsets. We also use some SET tolerant buffers. And so these are special buffers that are supposed to reduce the likelihood of a transient pulse occurring on your clock or reset or data lines. It gives us some more timing slack too, which is good to prevent TID degradation. We do have a hardened phase lock loop clock generator on board that goes up to about 300 megahertz. And then really the secret sauce is our radiation hardened storage cells. So these are custom designed cells that we made, and then we replace all the standard cells with these ones that we've painstakingly handmade. I'll just quickly go over it here. I wish I had more time to go into the physics exactly as how this works. But at this node, what we use is it's something called the transistor stacking technique. We have a number of published papers talking about this and why it's really efficient. So really all we do is that in the back-to-back inverters, these NMOS, PMOS transistors, we just double them. And because of this buried oxide layer and this electrical isolation at this node, it just really helps protect the latches from these transient effects. And we also do some really fancy layout-based techniques. So we're moving the transistors around. Some of them are closer together, some of them are farther apart, and this further reduces these transient pulses. And so here's a bit of a comparison between some of our cells and what a standard cell is. So with some moderate, kind of performance penalties, we can get like some super bulletproof cells. So the LAT threshold moves from about 1 to past 120. So these are bulletproof here. I'll talk about some of the experiments that we've done for irradiation. So pretty much all the campaigns, we have the same test setup. We have the device, it's connected to some programming PC, and then we have a monitoring PC to check data logs on the UART line, looking for errors, crashes, this sort of thing. The software that we run in it, so we do run sort of like your traditional matrix benchmark from CoreMark. We also do a bunch of other unit peripheral tests, like the UART SPI lines, the data controllers. There's a different number of unit tests that are gone through. We run it in either a looped or a non-looped mode. So in this non-loop, we just go through every single unit test one by one, come back to the beginning. In the looped, we run each unit test 100 times, and then we move on to the next one 100 times. So it takes a lot longer to go through the entire suite. We did 3 radiation campaigns. So one is just with alpha particles at our university with a small source. We did proton testing at Triumph in Vancouver. And then we also did heavy ion testing at Texas A&M University. And so here's some of the ions that we used for the cyclotron there. I'll talk about the alpha particles. So this is really simple. We just take a Mericium source, put it right over the die. All these particles are bombarding the chip. And so we saw that for the non-looped testing that I talked about before. There's no crashes or no failures for as long as we test it. Depending on if we scrub or not, we can get to see that our testing program's using a little bit over half of the memory in the device. And we do find some double bit upsets in unused memory. If we let it run for a long time and then we scrub the entire device, we do see some of these double bit upsets in the unused memory. Proton testing again, so we go up to a fairly high fluence, 105 MeV protons. The amount of upsets you get in the memory is a lot lower with the protons. That's sort of to be expected compared to the alpha particles. This testing was really boring. Nothing happened. no crashes or failures or this sort of thing. And we test up to about 200 kilorad, and the device was still functional. So for the heavy ions, this is where it gets a little bit more interesting now. So for our non-loop testing software that we run, again, it was like no failures or crashes or anything up to really quite a high LET and a good fluence. But when we start to do this loop testing, now we get to see some failures occurring in the device. So we'll go to some of the plots here. So on your left here, so this is the sort of traditional Weibull curve you see in terms of single event effects for a memory array. So the per bit cross section gets higher as the particle LET goes up, and eventually it saturates. But when you look at the device Cepheid cross section, the double bit upset cross section, it kind of stays relatively flat regardless of the particle LET. So this is something that we usually don't see. It's rather interesting and a little bit strange. Here's just some more plots showing the breakdown for how much time is spent on each unit test to how many upsets we're seeing on those tests. So there isn't a one-to-one correlation. It does seem like some unit tests are more likely to crash than others. And then in terms of the failure codes that we see, and we're able to pull off the JTAG from the device, I mean, the vast majority of them are just general IS exception errors. This is just like the program counter or some instruction code has just become like undefined, or it's gone to a null value, and the device just doesn't know what to do, and it just halts. There is a small number of failures related to the free RTOS operating system that was running the software, but most of them are just this general IS exception. And so I'll try and wrap it up here real quick. So for the proton testing, we did find that with the hardening techniques that we apply, there's no failures for either testing mode we did. It's a good TID tolerance, but now for the heavy ion testing, we do see that the software running on it has a strong dependency on whether or not the device will crash or not. So some kind of concluding thoughts and summaries. It does seem like the Cepheid rate tends to be more dependent on the software rather than the particle LET, which is a little bit strange. But this kind of suggests to us that the accumulated memory errors is really what's causing the device to failure. It's not necessarily upsets or bit flips happening in the core peripheral circuitry. And so understanding the whether the device will fail is kind of more dependent on the per bit cross section rate, as well as what the flux rate is, the particles, the environment that's in, and what kind of software is being run on it. So just to wrap it up with some future work, so we do plan to do some more probabilistic models to understand the failure rate of the device a little bit better. We do plan to do this pulse laser and microbeam testing. So with this, we can selectively irradiate just the memory, just the core circuitry, individual pieces instead of having the entire device irradiated. Hopefully, we can learn some more interesting things that way. It does plan to be a payload aboard our next CubeSat at the university, so hopefully we can get some flight time. That'd be really exciting, really cool to have another chip, RISC-V in space, right? And then it is on the back of our mind some sort of potential commercialization for either some of the underlying IP or technology that we've developed or the device as a whole. So if you're interested in that, you can maybe find me afterwards, and I'd like to chat with you. So thank you very much for your attention. I'd like to thank also all of our collaborators and research partners that made this work possible.